In this video, we're going to be solving some problems for Fluids, Unit 8 and AB Physics 1. 3 objects of identical mass attached to a string are suspended in a large tank of liquid as shown above. Must all 3 strings have the same tension? Justify your answer. So, for this question, part A, our answer is no, not necessarily. That's because each object is in equilibrium. So that means that the upward forces must balance the downward forces. So if we draw the FBD, we have an upward force of tension, and we also have a downward force of gravity, but we also have a upward force of buoyancy that's pushing the object up. Here, same thing as well. And same for object C. With the FG, which is the weight. So we know that those balance out. For each object, we can write that Newton's equation. So the summation of forces is equal to the mass times acceleration. So we know that we have an upward force of tension and an upward force of buoyancy, and that's going to equal to the mg. That's equal to the weight. So that means that T, your tension, is going to be equal to mg minus FB if you subtract FB from both sides. And we know that the M is going to be identical because it says in the question that we have 3 objects of identical mass attached to the strings. So that means that we have the same weight. Since weight is only equal to the mass times gravity, and this whole entire thing is going to be constant on Earth. Gravity is constant and mass is the same. So our buoyant force, FB, we'll highlight FB here. So for our buoyant force, FB, this is dependent on the volume of the fluid that is displaced. We know the formula for buoyant force is equal to rho of the liquid, V times G. And since the objects have different shapes and volumes, they don't necessarily displace the same amount of liquid. Because buoyant force is dependent on the liquid displaced, that means that FB can be different. Therefore, the tensions could be different. Now we're asked to calculate, or for object, let's do part B. So object A has a volume of 1.0 times 10 to the negative 5 meters cubed and a density of 1,300 kilograms per meter cubed. The tension in the string to which the object A is attached to is 0.09 newtons. Calculate the buoyant force on object A. So let's actually make some more room here. So for part B, we're given that the volume of A is equal to 10 times 10, or 1.0 times 10 to the power of negative 5 meters cubed. The density of A is equal to 1,300 kilograms per meter cubed, and the tension is equal to 0.0098 newtons. So we're going to use our equilibrium over there, which was T plus FB equals mg. And if we solve that for FB, we have that's equal to mg minus T. So first, we can take this equation, move this over here. We are going to find the mass of the object A. So to do this, mass is equal to rho times V. And here, rho is 1,300 times 1.0 times 10 to the power of -5. And this is equal to 1.3 times 10 to the power of -2 kilograms. And now we can find the weight. So weight is equal to the mass times gravity. So our mass is 1.3 times 10 to the power of -2. And then we multiply that by our 9.8, and that's going to give us 0.1274 newtons. For buoyant force, we have the formula by using this form of the rearranged form here. So we can take this, move this here. If we solve for our buoyant force, this is equal to 0.1274 if we multiply mg, right there, that was our weight, and subtract our tension, which is 0.0098, we'll get 0.1176 newtons. So that's the buoyant force. Now for part C, we're asked to calculate the density of the liquid. So the density formula, we can use FB and then isolate for density. So you'll have density of the liquid times the volume times gravity. And then we want to solve for our density. So we're going to have density of the fluid is equal to the buoyant force. We can divide both sides by volume and G. And then you get FB is equal to, or density of the liquid is equal to the buoyant force over the volume times gravity. So now all you do is substitute in your values. We have 0.1176, which we found over here, and you can divide that by 1.0 times 10 to the power of -5, and we multiply that also by G, 9.8, and then if you plug this into your calculator, you're going to get 1.2 times 10 to the power of 3 kilograms divided by meters cubed. So that is our density of the fluid, our liquid. Now let's move to our second question. 2. Blood has a specific gravity 1.0. Specific gravity means how dense it is versus water. 1 means the same density as water. The flow speed of blood in an aorta is 40 centimeters per second. The cross-sectional area of the aorta is 2.0 centimeters cubed. Calculate the mass flow rate in grams per second of blood in the aorta. So let's start with 2A. Let's write down what we were given. So our specific gravity is equal to 1.0, which is equal to the density of water. Density is equal to 1,000 kilograms per meter cubed per water in blood, and that's equal to 1 gram per centimeter cubed. We were also given that our aorta speed was equal to 40 centimeters per second, and our aorta area is 2.0 centimeters squared. So in order to find the mass flow rate we have to know that this is going to be equal to our density times our volume flow rate. So let's first find what our volume flow rate is. So this is equal to area times V, our speed. So this is going to be 2.0 centimeter cubed area times 40 meters or 40 centimeters per second, which was our rota speed. And this is equal to 80 centimeters cubed per second. And we know that our density is equal to that 1.0. That means that we can just substitute that in for the mass flow rate. So we have our density as 1 gram per centimeter cubed, and we can multiply that by the volume flow rate, which is 80 centimeters cubed per second, and this is gonna give us 80 grams per second, because you can see that centimeters cubed there cancels out, and we're left with the units of grams per second right there. So 80 grams per second is our answer. For part B, we're asked, assume the aorta branches to form a large number of capillaries with a combined cross-sectional area of 3,000 centimeters cubed. What is the flow speed in the capillaries? So for this, to be, we're looking for the flow speed in the capillaries. So we can use the continuity equation, which states that area 1 times volume 1 is equal to area 2 volume 2. So what we want to find is in the capillaries, we have a different speed. So we're given one speed, which is V1. So we can solve for our second speed, V2. And we have 3,000 centimeters cubed. So we can use that area as well. So we're going to take this and solve for V2. V2 is going to equal to A1 V1 divided by A2. V2 is going to equal to area 1, which was 2.0 times our V1, which was 40, and we can divide that by 3,000. This is going to give you 0.0267 centimeters per second if you plug that into your calculator. So for our next problem, we're asked, what does blood flow faster in capillaries or in the aorta? Does this make sense? So for part 2C, we know that the aorta speed is equal to 40 centimeters per second, and our capillary speed is equal to 0.027 centimeters per second, which is much lesser. So we can say that our blood flows much faster in the aorta than in the capillaries. Our question is if this makes sense. And we can say yes, it makes sense because capillaries have a much larger total cross-sectional area than the aorta. And for an incompressible fluid, we have a continuity statement, which is AV is going to be constant. And that means that when area increases, that means that speed must decrease in order for this to stay a constant product. For example, if you have 2 times 4 is equal to 8, and then you change the 2 to a 4, you're going to have to decrease that second number to a 2 to make it equal to 8. And they don't necessarily have to be 2 and 4. You could have, like, a better example would be 12, or a better example would be 6 times 2 is equal to 12. And if you decrease 6 to 3, you would have to use a 4 and increase that second number to still maintain 12. So that's basically what it means. It has to, if you adjust one, the other one has, if you increase one, you have to decrease the other one. And we know that biologically, blood should move slowly in capillaries to allow time for exchange of oxygen, nutrients, and waste. So that's it for question 2. For question 3, water flows through a section of a pipe with a diameter d, with a constant volumetric flow rate z, and a linear velocity v1. The water transitions to a section of pipe with a diameter that is d divided by 3. Derive an expression for the flow rate of the water in this more narrow section of pipe in terms of z. So we want flow rate in terms of z. So we have to think about what we are given. We have a closed system and we have an incompressible fluid. When we have these conditions, that means that your volumetric flow rate will be constant. So your narrow section has the same flow rate as the wide section. So that V, or we can say Z because that was what our speed was represented as the narrow is equal to Z. So your answer is Z. Now, we're asked to derive an expression for the flow rate of the water in this narrow section of pipe in terms of Z. We want the linear velocity in the narrow pipe part. So we have a continuity equation, which is that A1 V1 is equal to A2 V2. So we know that we had to find the area, but what we were given in this scenario is that this pipe is going to be having a diameter. Diameter implies that it's going to be a circle. So we can use area is equal to pi radius squared. And we know radius is equal to the diameter divided by 2. So we can find our original area, which is our original cross-sectional area. So if the diameter is going to be d, and d over 2, we can write A1 is equal to pi d over 2 squared. Now we can find the narrow area. The narrow area is having a diameter that is d over 3. So A1 is equal to that. So that's going to be pi times the radius squared, and the radius is equal to the diameter divided by 2. But here our diameter is equal to d over 3, so you have to remember to divide that by 2. So r is going to equal to d over 3, and then you can take the reciprocal of that and multiply it times 2. Or, yeah, so that's going to be d over 6. So we can write d over 6 there and square that. Now we can compare the areas with the ratio. So a1 over a2 is equal to pi d over 2 squared divided by pi d over 6 squared. And we can cancel out that pi. So we have d over 2 squared divided by d over 6 squared. And that's going to be d squared over 4 if we use that square. And then we have d squared over 36. So we see that we have d squared both present. We can cancel that. And then we can move 36 to the top, and then you're going to move 4 to the bottom. So 4 is going to be here, and then you have 36. And 36 over 4 is equal to 9. So that means your ratio is scaled by a factor of 9. So a1 is equal to 9 times a2. So if we solve for v2, using our continuity equation, a1v1 is equal to a2v2. v2 is, if we have to solve for v2. So v2 is equal to a1 over a2 times v1. And we know that v2 is equal to 9 times v1, which was the ratio. a1 over a2 is a ratio that we just solved for here. So that's going to be our area. v2 is equal to 9v1. So v narrow, we can say, is 9 times v1 by using v narrow instead of v2. So for our next question, in a refinery, ethanol fuel is flowing in a pipe with a velocity of 1.2 meters per second at atmospheric pressure, 1 times 10 to the power of 5 pascals. The refinery needs the ethanol to be at a pressure of 2 atm, 2 times 10 to the power of 5 on a lower level. How far must the pipe drop in height in order to achieve this pressure? Assume the velocity does not change, and the density of ethanol is 789 kilograms per meter cubed. So we're going to use Bernoulli's equation, and let's make some room here. This is for, so we're going to have Bernoulli's equation where we have energy. So we have P1 plus rho g y1 plus 1/2 rho g v1 squared is equal to P2 rho g y squared y2 plus 1/2 rho v2 squared. So because we know our v is not going to be changing, because we're assuming velocity does not change, that energy term is going to cancel out because v is constant. So v1 is equal to v2. So we can simplify that to P1 plus rho g y1 plus P2 plus rho g y2. We can subtract our P1 from both sides, and we can subtract this P1 here, and we're going to get, we can actually leave that there. So we're going to leave that y1 there, subtract y1 here. So that's going to give us P2 minus P1 is equal to rho g y2 minus y1. Since we're looking for the drop in the height, we can set that equal to h. And that's going to be y1 minus y2. Or y2 minus y1. So let's actually say y2 minus y1. That matches there. So now we can substitute that in for the height. So then we can solve for h, and then we just plug in with our values. We were given that P2 was 2.0 times 10 to the power 5, and P1 was 1.0 times 10 to the power 5. So we can divide that by density, which we were given was 789, and our G, which is 9.8 on Earth. You plug that into your calculator, you get 1.13 meters. Okay, so for question 5, 2 students observe water flowing from left to right through the section of pipe shown above. Further down, the pipe decreases in diameter and increases in elevation. The water exits vertically on the right. At point A, the water has a speed of 0.5 meters per second and a pressure of 2.0 times 10 to the power 5 pascals. The density of water is 1,000 kilograms per meter cubed. Students disagree about the water pressure and the speed at point B. They make the following claims. Student Y claims that the pressure at point B is greater than at point A because the water is moving faster at point B. Indicate any aspects of student Y's claim that are correct, and indicate any aspects of student Y's claim that are incorrect. Support your answers using physics principles. So for let's actually look at what we have in the scenario given our situation and not looking at the students so far. So at point A, we have a diameter that is 2.5 centimeters and a volume flow rate that is 0.5 meters per second. The pressure is 2.0 times 10 to the power 5 pascals, and our fluid is going to be slower here. So that means that the portion of Bernoulli's equation that has v in it is that 1/2 rho v squared. So we know that 1/2 rho v squared will be smaller. And we know that this is a lower elevation. And in Bernoulli's equation, that's the part where we have rho gy. So we know that that part of the equation will be smaller. The density of water is 1,000 kilograms per meter cubed, and this flows through the entire system. So that's going to stay constant. Then at the top, we know that the 1/2 rho v squared will therefore be larger. And we already know that the fluid up there flows faster, and that's the reason why it flows faster. We also know that it's higher up, so that rho gy, that y being the height, is going to be larger. And the diameter at this point is 1.5 centimeters as the cross-sectional area. So let's look at what is first correct. So student Y is going to be correct that the water speed at B is greater than at A. And that's because we have the continuity equation AA VA is equal to AB VB. So if we know that at AV, our diameter is going to decrease, or we know our diameter decreases, that means that area is going to decrease, area being pi r squared, and r being equal to d over 2 squared. So that d will decrease, and then the whole area will decrease. So if area decreases and we want to have a continuity where this is going to be something that is constant, not changing because it's a closed system and because we have a non-viscous fluid flowing through the pipes, that means that velocity B has to increase in order to multiply to the same product. And for student Y, what they're incorrect about is that the pressure at B is going to be greater than at A. That's because when we have Bernoulli's equation, that's P plus rho gy plus 1/2 rho v squared, and that's going to be something that's constant. So if we have a greater speed, if we have rho b, we're going to have a greater speed and a greater height at point B. So that means that at a greater speed and height, that means that the pressure B is going to be less than the pressure A. Now, let's look at part 3. So student Z claims that the speed of water is less at point B than at point A because by conservation of energy, some of the water's kinetic energy has been converted into potential energy of the Earth water system. Indicate any aspects of student Z's claim that are correct. So for this part, what the student was claiming was that at B, the speed is going to be less because at A, some kinetic energy is converted into gravitational potential energy. So let's see if that's right. And that's right because we have rho gy, and that term is going to have height in it. And if we increase the height, that's going to scale that term to be larger. We have an increase in height. So that means that the gravitational potential energy is going to increase. as it rises to a higher height. Now, what the student Z is incorrect about is that at speed B, it is going to be a less value than at speed A. And the reason is because the pipe is going to narrow from diameter 2.5 centimeters at point A and to 1.5 centimeters of a diameter at point B. And we know that for an incompressible fluid, we still have that continuity equation, which states that the area A times the volume flow rate A is equal to area B times volume flow rate B. So since we know that we are going to increase our area A, that means we have to decrease volume A. And on the other side, because we know we already decreased our area B, that means that we have to increase volume B. Or not volume, our velocity B. And that's because of our continuity equation. So that's those parts. Let's move on to part B. So calculate the following at point B. We want to find the speed of the water and also the pressure that is inside of the pipe. So we're going to find the speed of water at B first. So this is 5B1. We're going to have the continuity equation because the continuity equation has our speed in it. So that's going to be area A times our volume A is equal to area B times a volume B. And because we have a circular pipe, because we were given diameter, we can assume that it's a circle. Area is equal to pi times the diameter divided by 2 squared. So if we substitute that in, we have area A is equal to VA is equal to our area B. So we can say DA. Or we can actually take the ratio of area A over area B. Area A over area B is going to be dA over dB squared. That's because we had that pi dA over 2 and then pi dB over 2 squared. And we can cancel out everything else. So we were just left with this. Actually, let's leave that square in because we didn't distribute that square yet, so we need to. So now we can take that and substitute that into our equation. So we had VB, this was area A, area B. If we isolate both sides for VB, that's going to be A over B, and we're going to be left with VB is equal to that AA over AB. So that's where we got that ratio from here. And we know that that ratio is equal to this. So we can just substitute that in. So that's going to be the volume flow rate A, dA over dB squared. Now all you have to do is just substitute in your values. VA was 0.50. And we have 2.5 over 1.5 squared. And this is going to give you approximately 1.39 meters per second for your volume flow rate at B. Now we're asked to find the pressure in the pipe. So that's going to be 5B2. And to find the pressure at point B, we're going to use Bernoulli's full equation. Bernoulli's equation states that pressure A plus rho G YA plus 1/2 rho VA squared is equal to pressure at point B plus rho G YB plus 1/2 rho VB squared. What we want is to solve for pressure B. So pressure B is equal to pressure A plus rho G YA minus YB plus 1/2 rho VA squared minus VB squared. So all we did here, just to backtrack, we subtracted this term and this term. So this canceled out. Now, we can rewrite this as this expression here is equal to our pressure at point B. So what we see here is that we could factor out this rho G because we have a rho G here and a rho G here. This is actually missing a G. That's going to be rho G. So we can factor that out, and then we were left with on the inside our VA, or our YA, YB here. So that was YB, and yeah, we had A, B there. Okay, now after this, so let's actually make this the same color as well. What we're gonna do is look at our diagram again. So we want to find the change in height from point A to point B. So YA is equal to 0. YB is equal to 5. So our YB minus YA is equal to 5 meters. But if we want YA minus YB, that's equal to -5 meters. So we have to substitute this into our equation. Let's substitute everything in. We have 2.0 times 10 to the power 5 for pressure A, plus 1,000 as our density, times 9.8 times -5, plus 1/2 times 1,000, 0.50 squared minus 1.39 squared. If you plug this into your calculator, you're going to get 1.5 times 10 to the power 5 pascals.